Up to this point, most of the molecules we've talked about, we give you the chemical formula to start with. But if you are a chemist and you make a new compound, you don't know, beforehand what the chemical formula is. But what you can often figure out, and we'll talk about this in just a little bit, you can figure out the mass percentages of different elements by separating them by different ways. Undergoing a chemical reaction, seeing how much carbon you get, how much hydrogen you get, how much oxygen you get, or other things. And so that sort of data is something you can use to figure out what's called an empirical formula. This may not be the exact chemical formula, but it is the one that you get based on experimental evidence. And you need additional information to figure out whether you need to, say, multiply. It gives you the relative ratios, but as an example, maybe you find you have a molecule that gives an empirical formula of C2H5, but the actual molecule is double that, C4H10, if you multiply everything by 2. So this would be the empirical formula here. This would be the actual chemical formula. And you would need some information to know that you need to multiply this by 2. So the formulas we'll be finding through this method that we're going to talk about in this video will only give you this first version, which may be the correct formula. You may not need to multiply it by 2, but you don't have enough information from what's told you in just a percent composition to figure this out. Okay, so just to give a little bit of context about why we're doing this, what's the purpose of finding these empirical formulas, and what you may need to do additionally to figure out the actual chemical formula. Okay, so the best way to do this is by an example. So let's imagine that we have a compound. I've got some numbers here, and we get the following percent composition. We know that it is 28.58% carbon. We know that it is 3.6% hydrogen, and that it has 67.82% fluorine. And so this is sort of, we're going backwards of what we did in the previous videos, where we were looking at a chemical formula and finding the percent composition. Here we're going the other way around. Now, how do we do this? So remember, these are percentages based on mass. So here's the process we're going to go through. We're going to pretend or assume that we have 100 grams of this compound. We could pick a different number. 100 makes it easy because these are given us as percentages per 100, so that makes it very easy to do calculations. So if we have 100 grams of this compound, we can find what's the mass of each element. And here we're just going to use directly these percentages that are given to us right here. And so since this is out of 100, we can say, well, for carbon, we have 28.58 grams. That's 28.58% of 100. For hydrogen, we have 3.60 grams. And for fluorine, we have 67.82 grams. Great. Now the next step we need is to use our idea of the mole to go from masses to numbers of atoms, or moles of atoms. And so the next step is to take these masses that we have and convert them into number of moles. And that gives us a way to compare what's actually there in an empirical formula or a chemical formula. Right, there we're thinking about numbers of atoms or numbers of moles of atoms that are in a particular compound. So the next step here is to convert to moles. As you can see, this is this is something we worked on at the beginning of the chapter, and this is something we're going to do a lot of throughout the class, and is the key to stoichiometry. Always go back to moles. Okay, so for carbon, we can take this 28.58 grams. We're going to need to divide by the molecular weight. We've seen this 12 grams per mole show up a lot, right? And so we know we need to divide because we need the grams to cancel. I can't do this one in my head, but we get 28.58 divided by 12.01, and we get a value of 2.380. And this is how many moles we have in 100 grams of this compound, moles of carbon. And we can repeat that for hydrogen and for fluorine. So for hydrogen, we're going to have 3.60 grams. Again, we'll need to divide by the atomic weight, 1.008 grams per mole. Again, our grams cancel. Put this into the calculator. 3.6 divided by 1.008 gives us 3.57 moles. Again, we're seeing that hydrogen, because it's really light, even though there's not a lot of mass, there's more moles of hydrogen than carbon in this molecule. And then finally fluorine, which is our last one. We have 67.82 grams. Fluorine is not one that I have memorized, so I'm going to look over here in the periodic table. And that is 18.998. All right, put this into the calculator. 67.82 divided by 18.998. Nope, not times. It's like that number seems a little too big. And we get 3.57. Now, it's not a coincidence that these numbers are the same. This is a consequence of the fact that there must be equal number of atoms of hydrogen and fluorine in this compound. Okay, so now we've converted to moles, but this doesn't give us an actual formula. I mean, we could write a formula. It's just not a very satisfying one. It doesn't give us whole numbers. We could say, well, in our molecule we have carbon 2.380, hydrogen 3.57, and fluorine 3.57. But that's not right? We want these to be whole numbers. We want to know how many atoms is in a molecule. We can't have 2.38 carbons in a molecule. And so what we do here is we want to get these to whole numbers, and the easiest way to do this is to take whatever's the lowest value. So you take your smallest number. So in this case, that'll be our 2.38 for our carbon, and then divide everything by that number. Divide all values by that number. The purpose of this is to find the whole numbers, right? If we divide our lowest number by itself, it's going to be 1, and then everything else should be whole numbers or fractions relative to that. So let's give that a try. So we'll move this way so I still have the numbers here. So for carbon, we'll have 2.380 divided by 2.380, which gives us 1. For hydrogen, we'll have 3.57 divided by 2.38, and fluorine's going to be the same, 3.57 divided by 2.38, and our moles will cancel, just skipping writing those units down. All right, so we get 3.57 divided by 2.38, and that gives us 1.5. So we don't get exactly a whole number, but we get something that's a multiple of a whole number. So if we want this to be a whole number, 1.5, and we can only do this by multiplying or dividing. In this case, we'll need to multiply. So if we multiply everything by 2, those halves will go away, and we'll get 2, 3, and 3. So that's the final step. The final step is if you don't, at this step, get whole numbers, multiply to get whole numbers. All right, and these now are the subscripts that'll go into our empirical formula. So the empirical formula for this compound that we've been looking at is C2, need my pen, C2H3F3. This is our empirical formula. So this is the final answer that we have, is that our compound is C2H3F3. Now, this probably is not the actual formula. We may need to get the actual chemical formula for this compound. We may need to multiply by whole numbers. And we don't have enough information to know that, to know whether we need to multiply by whole numbers or not. That has to be provided by some additional information. But this is how we can get empirical formulas from percent composition data. And so we'll get some more practice with this in class, and you also get some more practice with this on your homework.